Okay, so for this example, we have 4 constraints, and we have to maximize one optimum function, z equals 3x plus 5y. So I'm only maximizing this. I don't need to work about the minimum. All I care about is the maximum for this problem. But I need to graph all of the constraints. So my first constraint that I'm going to work on is x plus y is less than or equal to 10. So I'm going to put that into slope-intercept form by moving the x to the other side. So that gets me y is less than or equal to negative x plus 10. This gives me an m of negative 1 over 1, a b of 10, and I also note that because it's less than or equal to, it's a solid line, and we're shading below. So I'm going to go to 10, 1, 2, 3, 4, 5, 6, 7, 8, 9, 10 on my y-axis. Then I'm going to go down one, right one, down one, right one, all the way off my picture. I can draw a solid line here, and I'm going to shade below. So I'm just going to put some arrows to the below side and move on to my next problem. The next problem is y is less than 1/2 x plus 7. So my m is already in slope-intercept form. My m is 1/2, my b is 7, and because it's less than or equal to says it's solid, less than says it's below. So I'm going to go to 7 on my y-axis, 3, 4, 5, 6, 7 right here. I'm going to go up 1, right 2, up 1, right 2, all the way off my picture. Now I've already crossed the orange line, which is important, and that's a corner point. It's a solid line, and I'm shading below. Okay. Our next problem, I'm going to do in green, our next constraint, x is greater than or equal to 0. Now, x is greater than or equal to 0 is a Vux problem. It's a vertical line at 0. And because it's a vertical line, I can't shade above or below, can I? It is a solid line, but I'm going to be shading to the right because you're comparing to x. Because there is no y, we're comparing to x, not y. We're going to shade left or right. X is greater than is to the right. And then our last problem, I'm going to do in blue here. Y is greater than or equal to 0. Again, it's solid. Because it's greater than y, it's above. And this is a Hoy problem. So it's a horizontal line at 0. Now, x is greater than 0, y is greater than 0 is a very common constraints for linear programming problems because we're talking about real-world things. We might be talking about numbers of bananas, or we might be talking about revenue, or we might be talking about the number of items you're selling. So in that case, we often talking about things greater than or equal to 0, which is why drawing the quadrant 1 graph, do you see how my axes are skewed towards the first quadrant so that you can see more of the first quadrant. Our next step is to graph to shade the feasible region. So I'm going to shade my feasible region here where the arrows are all pointing in. And then I'm going to list all my corner points. So the corner points that I see are 0, 0. Then I have one where the blue and the orange intersect. That's 10, 0. Then I see where the orange and the purple intersect, and that looks like 2, 8. And then my last corner point is at 1, 2, 3, 7 on the y-axis, which is 0, 7. So those are my 4 corner points listed in any order. It doesn't really matter. So when I try to go maximize, I'm going to be plugging in those values. So I have 3 times 0 plus 5 times 0, and that gives me 0. The next one I'm going to be plugging in 10, 0, so 3 times 10 plus 5 times 0, and that's 30. The next one I'm plugging in 2, 8, so 3 times 2 plus 5 times 8, and that's 40 plus 6, that's 46, that's our biggest so far. And then the last one is 3 times 0 plus 5 times 7, that's 35 plus 0, which is 35. So my maximum looks like 46. Okay, so 46 is my max. Where does it occur? It occurs at 2, 8. So I'm going to write my answer. I have a max of 46, and it occurs at 2, 8. That is the most complete way of giving the maximum. For our next problem, we have some more constraints here, and we're trying to minimize this time. Okay. So we want the smallest number from the optimizing function. I have 4 constraints. The first constraint I'm going to do in purple. So that's negative 2x plus 5y is greater than or equal to 20. So I want to solve this for y first. So I'm going to move the 2x to the other side, making it positive 2x. We get 5y is greater than or equal to 2x plus 20. Notice the inequality doesn't change because I didn't multiply or divide by a negative. So that gives me y is greater than or equal to 2/5 x plus 4. So my m is 2/5. The b is 4. I have a solid line and I'm shading above. So I'm going to go to 4, up to right 5, up to right 1, 2, 3, 4, 5, 1, 2, 3, 4, all the way off my graph. That's off there. I can connect this with a solid line, and I'm shading above, so I'm going to just put a couple arrows here to remind myself later that I'm going to be shading above. The next constraint I have is already in slope-intercept form. Y is greater than or equal to negative 1/2 x plus 13. So the m is already negative 1/2. My b is 13. It's a solid line because it's or equal to, and because it's greater than, y is greater than, it's above. So I'm going to go to 13. And from there, I'm going to go down 1, right 2, down 1, right 2. Looks like I intersected the purple line. And I draw a solid line. And I'm going to be shading above. Okay. And our next equation, I'll do in green, which is x is greater than or equal to 0. So that's a vux. That's our common one, where we have a vertical line on the y-axis, and we're going to be shading to the right. It's a solid line. And the last one I'll do in blue. That's a Hoy problem at 0, which basically is just telling me that we're talking about real world first quadrant values. So that's horizontal line at the x-axis pointing up. So the feasible region here, which satisfies all of the arrows, is this region up here. Now this one is an interesting problem because it's unbounded, because we keep going up forever and to the right forever. So let's identify some corner points. I have a corner point at 0, 13 right here. I have another corner point right there. I'm going to have to count 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 1, 2, 3, 4, 5, 6, 7, 8. I have 10, 8. And that's it, okay? All the other values just keep it going up forever. And because it's going up and to the right often, we're not going to have a max, but it doesn't really matter because all I'm trying to do is minimize, right? So if I'm trying to minimize, I have z equals 6 times 0 plus 3 times 13. That gets me 39 plus 0, which is 39. And the other point, I have 6 times 10 plus 3 times 8, and that gets me 60 plus 24, which is 84. So I'm looking for a min. If it's at a corner point, it's going to be the 39, but let's kind of identify, maybe it's not, maybe I could be wrong. Maybe let's pick another point to see if the values are getting bigger or smaller. So I just picked a random point out here, 2, 3, 4, 5, 1, 2, 3, 4, 5, 6, 7, 8, 9, 12, 13, 14, 15. I picked 5, 15. If I plug in this non-corner point, if I'm continuing to get bigger, then I won't have a max. If I'm getting smaller, then I'm not going to have a min. So I have 5 times 6, which is 30, and then 3 times 15, which is 45, which is 30 plus 45 is going to be 75. Notice 75 is bigger than the 39, and so I'm not getting smaller at all. In fact, when I keep going out this way, I'm going to get bigger and bigger and bigger and bigger. So do I have a min? Yes, I do. I have a min at 39. It occurs at the point 0, 13. This 75 tells me that things are going to start getting bigger here, not smaller. So I have a min. The min is a 39. It occurs at the point 0, 13. Okay. Our last question here is, using the same constraints from the last problem, try to maximize 2, 9. So I'm using the same corner points. I'm not going to regraph again. So I have z equals 2 times x. So I'm using these corner points. My x is 0 plus 9 times 13. And that gets me 0 plus 117, which is 117. My next point, 2 times 10, that's 20. And 9 times 8, that's 72. So that gets me 92. So notice this time I'm trying to maximize. Okay, because I'm trying to maximize, I'm trying to find the biggest value. So what if I tried another point, like the 515? 2 times 5 plus 9 times 15, that's going to be 10 plus 135, which is 145. This is bigger, isn't it? So because it's bigger than 117, we don't have a max. The max would occur at the corner points if it existed. But the fact that I found another point in the feasible region that's even bigger than it, this tells me that we have no max at all. So some books might say no solution for this problem. If you don't have a max, you might be asking, you might need to write no solution. And this concludes our lesson on solving linear programming problems graphically.